Okay, so today we're going to talk a little bit about limits, and I want to go back to a function that we were looking at earlier in the calculator skills section that's sine of x over x. So our function is f of x equals sine of x over x. And the problem with this function is at 0. Nothing can be divided by 0. It's undefined to be divided by 0. And so we can see that in the calculator when we set up the table that there's an error. And that's the calculator's way of telling us that the function is undefined at 0. However, if we look at a graph, it looks like the function is actually approaching some value from either side. And it turns out that this value looks like it's 1. That the value of the function is 1. And so this is the idea of a limit. The idea is that I could have a function that, say, isn't defined somewhere. Here, this is called a point discontinuity. Where just that one point is missing. So the function at some value c is not defined, or the value x equals c is not in the domain. These are all ways of saying the same thing. So the function can't be evaluated there, but if we look from each side, as we get really close to but not touch that point, the function does appear to be approaching a value. That's the idea of a limit. Now, it's still possible a function can have a limit and be defined there. So both cases are okay. It's okay for the function to approach a point and have that point be the same. It's okay for the function to approach a point but have that point actually be missing. And it's also okay for us to have a limit like this, like a piecewise function where we have a jump discontinuity. And in this case, the limit does not exist. And we'll talk about this in a second, because you can see that the function is approaching two totally different values. So in that case, that is a situation where a limit doesn't exist, because again, the function is approaching two totally different things. And there's one other scenario I want to show you where we have a function that's got a point discontinuity, but it's defined piecewise with a point like somewhere else above the function. This is okay. The limit exists and has a value because at both sides we're approaching the same thing, but it's still okay that the function itself takes on a different value. Okay, so your book gives a pretty complicated but very precise definition of what a limit is, and you're not, in the AP test, you're not required to understand what's going on there. So I want to give you kind of a summary of what that means. It's more important. The limit of a function is a value it approaches, but does not necessarily take on. So we'll say as x approaches c, but does not necessarily take on. Okay. So again, some examples here. The limit, here we would write the limit as f of x, or sorry, the limit of f of x as x approaches 1. So as we're getting closer to 1, which is here, the limit is equal to 2. We're getting close to the value 2. But keep this in mind, f of 1 is not defined, or we usually write it like this, just as shorthand, does not exist. So doesn't exist, or we could write undefined. That's okay. The function doesn't have to be defined there. The limit can still exist. We can still have a value for the limit. Same thing here. The limit as of the function f of x as x approaches 1 is equal to 2, but f evaluated at 1 in this case is here, is equal to 1. It's been defined piecewise as 1. And here we have a function that includes the value in its domain. F of 1 is equal to 2, and the limit of f of x as x approaches 1 is also equal to 2. So if we have a situation where we're trying to take a limit of a function that is continuous at that point, where that point is included in its domain, then we can just substitute. We can just plug the number in, get 1 plus 1 equals 2, and that's fine. Okay, over here this was not okay, because if we tried to evaluate at 1, we'd get 1 squared minus 1 over 1 minus 1, and that ends up being 0 over 0. We don't know what that is. So that's why it's undefined. So in this case, you're going to learn a bunch of tricks for taking limits later, but right now just keep that in mind. If the function's not defined there, you can't do substitution. You can't just plug in the number and see what the function is equal to there, because it doesn't work. One of the tricks that you'll learn is extended functions. So here we could factor the top, and we would get x minus 1 and x plus 1 over x minus 1. And so the extended function is x plus 1. So this is called an extended function because its domain is larger than we started with, okay? So that means that some of the answers we get from the extended function do not satisfy the original function before we did the simplification. We have to keep track of that. But in this case, the extended function can help us find the limit through substitution. I'd like for you to pause the video here and read through the properties of limits if you haven't already. The way you read this chart is basically here it's saying the limit as x approaches some number c is equal to a value L and another function g approaching the same point has a limit that's equal to the value m. And these are all the rules that we can have. If the two functions are added together, we can take their limits separately. So the limit of f plus g is the same as taking the limit of f and finding L, and taking the limit of g and finding m. Same thing with the difference. Same thing with the product. We can, instead of finding the limit of f times g, we can find the limit of f and find L, and take the limit of g and have m. If we have constants that don't depend on x, we can just leave them alone and take the limit of just the function. So we get k times L. And the quotient rule is one that we need to be very careful with, because the property works just like the ones above, except that we can only use this rule if the limit on the bottom does not equal 0. Okay? If the limit on the bottom equals 0, then we have to do something else. Same thing here. We need to make sure that our power function doesn't include a 0 in exponent. Let's use this as an example. Let's say that we have the limit as x approaches 3 of x squared. What this rule is telling us is that this is the same, it's equivalent to writing the limit as x approaches 3 of x and then squaring it. So we can take the limit of the function on the inside and then square it afterwards. And both of these would be, so x is actually defined at 3, so we can use the substitution rule, just put in a 3 and we'll end up getting 9. Okay, so make sure you review those properties. That's what we're going to be using in the rest of this lesson. Okay, so here we've got x, it's cut off, but I think that's x to the third plus 4x squared. I would just make up our own one because I don't know what this one is. So we're going to do x to the third plus 4x squared minus 3. And we're going to try to take our limit as x approaches c. So we're going to write the limit as x approaches c. Okay, so we can first start by using the sum and difference property. So we're going to have the limit as x approaches c of x cubed plus the limit as x approaches c of 4x squared minus the limit as x approaches c of 3. Now we've got a couple of different properties here. Here, this is the exponent property, and x cubed is defined at c. Basically, it's all real numbers, x cubed is. So we can just plug it in and get c cubed. 4x squared, we can pull the 4 out and just look at x squared. Again, x squared is defined at all real numbers, so we're going to have 4c squared. And then the constant rule says that the limit of a constant is just the constant. It doesn't depend on x at all, so it's always 3. So that's our answer. So you might be thinking to yourself, well, this seems really complicated for something that's very simple. And right now it is, but we'll see in just a few examples that we can bump into some limits that are not straightforward and need some more work before we can figure out what they are. So let's try another one. Let's do this. So we're going to do the limit as x approaches c of x to the fourth plus x squared minus 1 over x squared plus 5. So remember, before we use the quotient rule, we have to check to make sure that the denominator won't be 0. It's hard because we're using c and not a real number, but we can verify that because anything we plug in for x is going to be positive because we're squaring it. We're not dealing with imaginary numbers at all in this class, so we know the bottom will always be bigger than 0. So we can use that rule. So we're going to have the limit as x approaches c of x to the fourth plus x squared minus 1. And the limit, so we're going to take the limit of the top and the bottom separately. And again, we can treat this all as one function. So the top is a polynomial that's defined at all real numbers, and the bottom is a polynomial that's defined at all real numbers. So we can again use the substitution rule and say that this is c to the fourth plus c squared minus 1 over c squared plus 5, and that's our limit. So here we're saying that if we have any polynomial and we take the limit as f approaches c, we can just substitute in c. That's what that's saying. And again, if we have any ratio of polynomials, as long as the bottom polynomial is not equal to 0 when we plug in c, we can just do a substitution for the top and the bottom.